Best practices to avoid single points of failure revolve around proper use of multiple fault containment regions. To do this, first use hardware redundancy to provide multiple FCRs and hardware isolation between FCRs so that each will fail independently. Typically, each FCR needs to be an independent integrated circuit chip to avoid unforeseen coupling mechanisms within a single chip that can cause correlated failures across that one chip. This means that unless you have a chip that has been certified for the safety level you need, simply using a multi-core chip will not give you sufficient isolation even if the operating system promises some isolation between tasks. Software across multiple fault containment regions needs to avoid correlated failures. This is typically achieved by making at least some of the software perfect for practical purposes via using a high safety integrity level development process. The natural diversity between a doer and a checker may provide some benefit, but you cannot take full credit for it unless you've been very careful to design and prove independence of failures. A pattern commonly used in mission-critical embedded systems is the multi-channel architecture, typically in the form of a 2-of-2 cross-checking pair. The second commonly used pattern is the doer-checker pattern. A third pattern sometimes used is the safety gate added to a doer-checker pair. The pitfalls in avoiding single points of failure are numerous and sometimes quite subtle. Some big ones include 2 copies of the same software or even just similar software will often fail in exactly the same way because they have the same software bugs. Thus, you cannot assume independence of software failure without special effort. For practical purposes, the best way to deal with this is usually to use a high safety integrity level engineering process to make sure your software is perfect for practical purposes. It is important in a multi-channel architecture to make sure the system does not fail by always trusting one channel, even if that's the faulty channel. The safety gate architecture can have the same problem in that the gate can decide that it's always going to let the outputs through even if the checker tells it to shut down. In a doer-checker architecture, it is important to ensure the checker is actually working and has not failed in a way that just permits all outputs to go out whether safe or not. Often, the most difficult part of getting safety-critical designs right is looking for hidden causes of correlated failures. This could include hardware design defects on multiple chips, shared software libraries, defects in requirements used to design hopefully diverse components, a shared faulty time source, a shared faulty power supply, and the list goes on.